Let's talk about measurement error when using administrative data in pragmatic trials. Over the next few minutes, we will talk about what admin data represent, the meaning of misclassification and why it happens, and how measurement error can change your treatment effects and trial conclusions. The goal is to help you use these data with your eyes open, and to design your trial and analysis in a way that is defensible and transparent. Let's start with the core idea. Admin data measures coded events. Those codes reflect what was documented, interpreted, and then submitted for billing or for system reporting, surveillance, regulatory compliance, and health system management. So when you pull heart failure hospitalization or stroke events from a data set, you are not directly pulling biology. You are pulling a label created through a process. The key question is simple. Are we measuring the patient, or are we measuring the coding system? Keep that question in mind because it explains most of the issues we will cover next. So why do codes differ across places and time? Several forces shape what gets documented and coded. Financial incentives and reimbursement rules can influence what is emphasized. Audit pressure can make coding more conservative or more specific. Documentation quality varies by clinician, setting, and workload. Institutional culture matters too, because local coding practices evolve. Policy changes and updates to coding standards add time trends that look like clinical trends. Finally, the diagnosis hierarchy matters. Using the most responsible diagnosis is not the same as using diagnoses in any position. Bottom line, coding reflects systems and incentives, not just disease. Many admin data definitions have high specificity, meaning that if the code is present, it often represents a true case. But sensitivity is often modest, meaning you miss milder, atypical, or poorly documented cases. That has real consequences because you might underestimate the incidence of your event, leading to lower statistical power and even biased treatment effects. What are the implications of misclassification? The most common, and often considered benign, is called non-differential misclassification. That simply means the outcome is measured with the same level of error in the groups being compared. In other words, the chance of missing a true event or mistakenly counting a non-event as an event is similar whether someone is in the treatment group or the control group. A common rule of thumb is that non-differential outcome misclassification tends to pull effects toward no difference or towards the null. But let's make this more concrete with some examples. Here is the setup. We assume the exposure is measured correctly and the outcome is binary. We also assume the misclassification probability is the same in the treatment and control groups. The true 2x2 table is shown with counts A, B, C, and D. The true risk ratio compares the risk in the treatment group to the risk in the control group. Now, let's start introducing measurement error. For example, we might get some true positive cases getting recorded as negatives, and some true negatives getting recorded as positives. This is now our observed 2x2 table with star values. The equations here show how observed counts for cells A through D depend on the sensitivity and specificity of the algorithm used to capture the outcome. In this slide, we will walk through concrete numbers. Let's consider this simple, randomized trial example where each group has 10,000 participants. The true risk is 9% in the treatment group and 10% in the control group. The true risk ratio is 0.90. The 2x2 table shows 900 events in treatment and 1,000 events in control. The confidence interval excludes 1, and the p-value suggests a difference. This is our reference point, the truth before any misclassification. So let's see what happens to our treatment effect when the outcome is measured with some error. For now, we keep specificity at 100%, so there are no false positive cases being captured by our algorithm. But let's vary the sensitivity from 100% to 60%, meaning we miss 0% to to 40% of our events. Notice that as the number of observed events falls in both groups, the risk ratio stays at 0.90, but the confidence interval widens, meaning we have less precision since we have fewer observed events. So with perfect specificity, lower sensitivity mainly hurts precision and statistical power. Now let's reduce the specificity of our algorithm to 95%, meaning 5% of non-cases are incorrectly counted as cases in both groups. This is a big deal because the pool of non-events is large. Look at the second row. Even at perfect sensitivity, the observed risk ratio moves from 0.90 to about 0.934, closer to no difference. As sensitivity drops, the estimate moves further toward 1, and uncertainty increases. The takeaway is not that one metric matters more than the other. The takeaway is that false positives can dilute relative differences, and that dilution is more visible when the true event rate is low. At this point, you might be wondering, how accurate are common outcomes when we capture them using administrative data? The honest answer is, it depends on the condition and the context. Here are 3 cardiovascular examples. For congestive heart failure, stroke, and TIA, the sensitivity is often above 60%, with specificity around 99%. For heart attacks, sensitivity is often above 80%, and specificity is often above 90%. The point is not the exact numbers. Validity metrics can vary by jurisdiction, time, population, data source, and the specific code definition you choose. So whenever possible, look for validation evidence that matches your setting, rather than assuming results will generalize. This is an extension of the previous slide, but we're not going to go into all the entries in this table. Like the previous slide, the accuracy of admin code algorithms can vary depending on the diagnosis you care about. Pause the video and scan this table for outcomes that are relevant to your own study. As you do, ask yourself, do I have validation evidence that matches my jurisdiction, time period, and patient population? Or am I borrowing assumptions that may not hold? Now let's connect misclassification to analysis choices. We briefly touched on methods that estimate risk ratios, and we found that when specificity is at 100% and sensitivity drops equally in both groups, the relative effect can stay similar, but precision worsens. When specificity drops, false positives push estimates toward no difference in treatment effects. For rate models like Poisson or negative binomial models, similar logic applies if misclassification only changes the event count and not the follow-up time. Survival analysis adds complexity because timing matters. Missed events can behave like additional censoring, and false events can create failures at the wrong time. The big takeaway is that misclassification does not show up the same way in every model. So far, we have focused on binary outcomes, but many clinically meaningful outcomes can have 3 or more categories, like mild, moderate, and severe disease. For those types of outcomes, the usual bias toward no difference shortcut can break down. Misclassification can redistribute people unevenly across categories. If you collapse categories, you can distort gradients and dose-response patterns. And if movement is asymmetric, such as extreme cases shifting into middle categories, your effect can change in unpredictable ways. Again, the point is that multi-category outcomes need extra care, and you cannot rely on the assumption that bias tends towards the null. Beyond the impact of misclassification on our treatment effects, we also need to think about what is being captured in admin data and what gets left behind. Even when a code is technically correct, this data often misses the details like symptom burden, functional status, disease severity, laboratory values, and clinical reasoning. For example, a hospitalization record with a heart failure code does not tell you how severe the condition was. The other thing is that when severity is not recorded, the events you do capture often skew toward the more severe end of the spectrum, because severe cases are more likely to trigger hospital care, specialist documentation, and clearer coding. Depending on the condition, milder cases may never show up as a coded event at all. That means your analysis may be estimating the effect on a selected subset of captured cases, not the full clinical population you had in mind. So be explicit about what your outcome represents. Now let's talk about trends. A change in the incidence curve for a condition may reflect a real shift in disease, but it may also reflect changes in how events get captured. Coding shifts are a big part of that. Transitions in coding standards, policy changes tied to funding, updated clinical guidelines, and external shocks like a pandemic can all change documentation and coding behavior. But it is not only about coding. Incidence curves can also move because people change how they access healthcare resources. For example, fewer visits to the emergency department, more virtual care, longer waits, or shifting thresholds for admission can all change what shows up in administrative data, even if underlying disease risk is stable. That is why it is risky to compare across long time spans without checking whether the measurement environment changed. In pragmatic trials, this also matters when your baseline period uses one environment and your follow-up period uses another. So what do we do about all this? The main strategy is rigorous pre-specification. Define exact code lists, including versions and effective dates. Specify diagnosis position rules, such as primary diagnosis only versus any position. Define look-back windows for the history of previous illnesses and events. Decide how to construct episodes of care so that multiple claims or visits do not become multiple outcomes. And set washout definitions if you want incident cases. Pre-specification in your protocol and statistical analysis plan protects credibility, reduces avoidable bias, and makes your analysis reproducible and defensible. For any coding algorithm used, start by citing prior validation work that reports sensitivity, specificity, and positive predictive value for your measures. If feasible, do some internal validation, such as a chart review or linkage to clinical data. Then run alternate definitions, ones that are more restrictive versus ones that are more inclusive, to see whether conclusions hold. Finally, test robustness to misclassification using quantitative bias analysis. Bias analysis quantifies how measurement error could shift your effect estimate. That is beyond the scope of this module, but if you want to learn more and see practical tools, go to the link included on this slide. Let's wrap up. Admin data measure coded events, not clinical truth or biological reality. Codes reflect systems, incentives, and documentation practices, not just disease presence. Validity varies by outcome and context, so you should look for evidence that matches your setting. Your definition determines your event rate, bias direction, and power, so algorithm choices are not just technical details. And the final takeaway is simple. If you do not understand how the code is generated, you do not understand what you are measuring. Use transparency, validation evidence, and sensitivity checks to keep your pragmatic trial conclusions credible. If you found this helpful, hit like and subscribe. New modules drop regularly, and they build on each other.